We're really only focusing on a few topics: structure and bonding, which is review basically, simple nomenclature, just some simple examples. Based on the structure and bonding, we'll look at the reactivity trends, how aldehydes and ketones tend to react. Then really we're just going to focus on two areas of reaction out of the chapter, not all of the reactions in the chapter by far, but the reduction reaction and addition reactions, which I'm going to expand on only very slightly so that you can understand the concept of it and do less memorization, I think. The carbonyl group, if you recall, looks like this, and it's polarized. Remember, we used the Greek letter delta minus, delta plus to show that it's polarized, meaning the carbonyl carbon is electron deficient. Anytime something's electron deficient, it means it can accept electrons. That's going to help govern its reactivity. So something with a pair of electrons, and if you recall how we've been showing this with arrows, some pair of electrons can come in and form a bond to the carbonyl carbon, displacing a pair of electrons that was one of these bonds between carbon and oxygen, displacing it up onto the more electronegative oxygen, which makes sense because that's where electrons would want to go toward, a more electronegative atom. So you have bond forming, bond breaking. Aldehydes and ketones, being so similar in structure, both react this way. And really that's going to govern all of the reactions we see in this unit. Just as a refresher, aldehydes and ketones look like this. Aldehydes, what's implied is that there's a carbon continuing in this direction. And for ketones, carbons on both sides. Obviously, if you were to put an OH group here, you would no longer have a ketone, but you would have a carboxylic acid. Just thought I'd point that out. Some simple examples of naming. So, aldehydes end in al. Ketones end in one. O-N-E. What we have here then is a 1, 2, 3, 4, 5, 6. It's a hexanal. Hexane, except with the al ending because it's an aldehyde. Hexanal. It's one hexanal because the carbonyl group is at the 1 position, which is always going to be the case with aldehydes, if you think about it. Right next to it here we have a carbon chain that's 1, 2, 3, 4, 5 carbons long. There's a ketone at carbon 3, so it's 3 pentanone, pentanone. This is a cyclopentanone. And we number from the carbonyl, so as priority, so 1, 2, 3, it's a 3-methyl cyclopentanone. Over here we have benzaldehyde, which differs in this kind of nomenclature because it doesn't just end in al, but it's called benzaldehyde. That was from a unit or two ago. I don't remember now. We have a 6-carbon chain here. That's a ketone, so it's a hexanone. hexanone. And at the 5 position, there's a methyl, so it's 5-methyl. 2, squeeze a 2 in there, 2-hexanone, right? Because the carbonyl, the ketone, is at 2 position. That's pretty much the extent of the simple naming that I expect. You have to remember the different substituents still, like, you know, if there's an isopropyl group or a butyl, sec-butyl group, tert-butyl group, all those still hold. Clearly, if you have chlorine, bromine, fluorine, iodine, halogens, you can easily name those, like 1-bromo, this or that. So all the stuff we've known from before. Now into the chemistry more. My beef with the new textbook, McMurray textbook, is that it spends way too much time on naming, as if naming things is understanding them. It's really not. If you meet someone named Bill, you know their name, but do you understand them at all? No. So, a term that the book really should use at this point is the term nucleophile, which usually is an atom or a group of atoms that can form a new bond to something that's electron deficient, remember. In this case, a carbonyl carbon of an aldehyde or ketone, by donating 2 electrons to form the bond. That's really actually the definition of a Lewis base, except when we talk about a nucleophile, we're usually talking about bond forming. When you talk about a base, sometimes you mean that it's just something that pulls a hydrogen off of another molecule, which is actually bond forming if you think about it, but it's specific to just pulling off hydrogens when you say the word base. But a nucleophile is forming a bond to the carbonyl carbon in this case. Here's some examples of nucleophiles. We're going to focus primarily in this chapter on OH minus, a hydroxide ion, and just an H minus, a hydride ion. However, it's important to point out, and this requires another hydrogen there, I just noticed. It's important to point out that some of these species don't exist just floating around in solution on their own. So OH minus is often paired up with sodium, like sodium hydroxide, NaOH, right? But it's a salt-like thing, like you see so much in general chemistry, a minus plus salt, essentially. This is an amine. This can exist sort of floating around on its own, actually. But notice it's not negatively charged. It does have this pair of electrons that can go and form a new bond, though. And the OH does too, of course. I'm going to go over to, well, okay, now I'm going to go down here. So a hydride definitely can't exist on its own, floating around in solution. Can't exist on its own. So what do I really mean by that? In order to deliver a hydride, which is what this is called, new term, hydride, a hydrogen with a minus charge. Basically, if you look at this, it's a proton in the center of the nucleus with 2 electrons. It's a hydrogen with an extra electron, because normally hydrogen is just a proton and an electron, the simplest atom. You add another electron to it, it's now called a hydride. It needs to be delivered by, in a different form from a different species. So the typical sources of hydride delivery they're also salt-like things. Sodium borohydride and lithium aluminum hydride. The book doesn't specifically mention these. It just mentions hydride, and it almost kind of suggests that it exists on its own, which is bad. So these are sources of hydride, typical sources of hydride. These deliver the equivalent of an H minus. These deliver an H minus, very important. So really all you have to do is remember that. Sodium borohydride, lithium aluminum hydride. And I can write those out. Sodium borohydride, lithium aluminum hydride. Really just a description of what they even look like, if you think about it. Sodium, boron, aluminum. Okay, so let's look more and so finally, this one other example of a nucleophile, we're not going to get to for some time, but this is in fact the most important one because it can form new carbon-carbon bonds. And if you think about organic molecules, they're for the most part made up of carbon frameworks, carbon skeletons, they're called. So to create new carbon-carbon bonds is vastly more important than some of these other ones, which are also important. But we will see more on this a little later in the course. Important for forming new carbon-carbon bonds, really the ultimate in organic chemistry. And this is typically paired up with something else too, but we'll just see that later. So a reduction reaction. Here's a ketone reacting with hydride. Remember, this is going to be delivered by sodium borohydride or lithium aluminum hydride, but the bond forming reaction is just exactly like we described above. Bond breaking. And you see the new bond that's been formed, so you've added one hydrogen there. The other hydrogen comes from when the reaction is stopped, or quenched as we call it, where the oxygen, which now has extra electrons and is negatively charged, can pick up a hydrogen from water, or something like water, something that can give up a hydrogen in this way, and now you have your second bond to hydrogen. And so you have the net result of addition of H2 across what was a carbon-oxygen double bond, right? This carbon-oxygen bond was a double bond. You take, basically, the net reaction is you take one of those bonds away and you add two hydrogens across it. If you have an aldehyde, same deal. Exactly the same deal. Bond forming, bond breaking, new bond to hydrogen. Oxygen can pick up a hydrogen from a solvent or something else in solution like water. Another new bond. Addition of hydrogen H2 across what was the double bond. So this really should be pretty reminiscent of what we saw before. Remember this reduction reaction where we had alkenes adding hydrogen, and you added a hydrogen to each carbon of the double bond, and the double bond is no longer there, So make sure your product doesn't have any double bond left in it if you are doing a reduction in this way. The only difference here is that this is not a hydride reagent. It's hydrogen gas for alkenes. They literally bubble gas through the solution. The next video will be the only other one, and it will go into the addition reactions that really operate in very much the same way as what we see here, except that instead of hydride, you're going to have other nucleophiles, for example here, You could have an oxygen nucleophile, a nitrogen nucleophile, or in fact a carbon nucleophile, but we're not going to go into that in this chapter. That's it for this video.